So first, thanks to Mike for the invitation. And actually, I'm a bit embarrassed because there will be no iron, or basically no iron in my talk. So for some reason, I diverged in my presentation. But okay, I will put water, and I'm pretty sure that Monica will put a grain of salt after. So, so this will be fully safe. Okay, so but I wanted to show you some of the results we obtain on experiment and theory about water transport, but actually also ionic transport, but here we present only water, in very confined structures, in particular nanotubes. Okay, here it's molecular dynamic simulations, but we try to do real experiments. And by excitable there, I mean that you have excitation here in the solid. It's not a bare, rigid solid as we are used to think of in hydrodynamics, but you have, I don't know, electronic excitation, phonons, or whatever you think of. And actually, my talk, I would mostly discuss about what happens when you have this. But of course, when I was reading the announcement of the conference, I was, of course, this is quite important for me, the question of how you address, as a basic science guy, how you address industrial problems. And of course, this was pushed forward that Sam Edwards was actually very pivotal in this aspect. So I wanted to show you, at least in the 2 or 3 last minutes, how I try modestly to make the connection between basic science, what we do in our lab, and real applications. So, but let me start with nanofluidics. So so nanofluidics basically you study transport of fluids and ions in extremely small channels. So let's say basically below let's say 10 nanometers. And in the US they speak about single-digit nanopores, which is a bit fancy. But actually the great advance that we could do in this field is that using the nanotubes, okay, we know carbon nanotubes, boron nitride nanotubes, but also van der Waals assemblies, you can really design and fabricate systems where the confinement is below 10 nanometers and even down to a few angstroms. And so this you can do in a very controlled way, and then you can really measure things and quantify flows, etc. And actually, over the last 10 years, there have been plenty of results which have emerged in terms of dielectric anomalies, for example, superfast flows, anomalous ion transport, and a lot of non-equilibrium, nonlinear transport, etc., etc. And so that was, in some sense, worth the effort. And but one effect I would like to discuss, and this is how I entered in these excitable surfaces, is, of course, the weird behavior of nanotubes. And I mean, this is there for 20 years, basically. That when you look at the permeability of carbon nanotubes, and actually this started with carbon nanotube membranes over centimetric scales, you find that the permeability of the nanotube membranes is by orders of magnitude larger than what you would expect with, let's say, no slip condition or even, a small slippage. And actually, for example, I took this from a recent review from our American colleagues, and here you plot the flow enhancement, so how larger as compared to standard quasi flow you get, versus the carbon nanotube diameter, and you see that there is a very strong increase, and you see this is by orders of magnitudes. And actually, these are our experiments that we did in Paris, which I would like to discuss. But actually, this is really something which is basically not really understood. And in particular, what is not obvious is why does it depend so strongly on the carbon, on the diameter of the system. And this is something which you cannot explain by standard molecular dynamics, actually. And so in the group, so that's a result which goes back to a few years now. So we actually found a way to measure the flow inside a single nanotube. Because there, with the single nanotubes, you can control basically everything. You can control the size of the nanotube, its length, whether you have defects or not, etc., etc. And what we found is that, okay, here I plot the slip lengths. So the slip lengths, I will come back to it. but that's basically measuring the deviation to the Poiseuille flow. And so basically, a large slip length means a low friction. And actually, what you find with these slip lengths is that first, you have a huge difference between carbon nanotubes and boron nitride nanotubes. So, and this is very shocking because the boron nitride nanotubes has exactly the same structure, crystallographic structure as the carbon nanotubes, except that it's insulating. So only the electronic properties are differing, and you see a huge difference in terms of the friction on the surface. And second, this slip length, so the friction depends strongly on the radius. And actually, when you can plot this data that we found in another way, actually you can really plot the friction coefficient of water on the surface of graphite, on the surface of the nanotubes as a function of the radius. And you go, let's say, a flat surface is basically HOPG, so flat graphite. So you have a large friction there. Then you decrease strongly the friction when you reduce the radius, and in the range of tens of nanometers. And actually, graphene is around there. It's okay. Making experiments with graphene is actually very difficult because graphene is always deposited on something, and this pollutes the data in some sense. Especially, it's very sensitive on the underlying surface. But okay, this is okay. So that's the curve, and of course, you would hope to go to 0, and that would be the equivalent of superconductivity. But okay, let's keep it cool. So this goes back to, of course, to liquid friction. I introduced the slip lengths, and actually, for me, it's really revisiting this problem again and again. I mean, I started 25 years ago, and I always come back to this question. Anyway, so friction, actually, when you go from hydrodynamics, it's very simple. You have a hard wall, no slip boundary condition. When you go to the molecular pictures, okay, you have the boundary may be discussed in terms of the interaction of the water molecule with the surface. So let's say you have a van der Waals interaction and things like that. So that's what we put in standard molecular dynamics. Of course, actually, since the beginning of hydrodynamics, there was the introduction of the slip length and the generalization of the no slip boundary conditions, just because actually Navier didn't know what to impose. So let's assume it's partial slip. So and actually this slip length is really a measure of the friction coefficient. So because it's really this is a balance between the hydrodynamic stress and the surface stress, and the surface stress is proportional to the slip velocity. So I think lambda for me is really the physical quantity, and the slip length is just a convenient matter to plot it because you have the viscosity. And actually, some time ago with Jean-Louis Barra, we wrote a Green-Kubo relationship, and this was useful to obtain molecular estimates of these slip lengths. So that's the standard way you think of it. Now, I showed you the results for the friction, which was really anomalous. And so we tried many things and I couldn't figure out. So we said, why not going back to the underlying solid? So here in the experiments, we had multi-wall carbon nanotubes. So this is basically something in between graphite and graphene. So it has electron excitation. So let's go to this description. And actually, of course, we were dreaming of having a quantum effect there. And also this connected to these fabulous papers of John Pendry about what he calls quantum friction. So basically, the fact that if you have two flat surfaces, you may still have friction because of van der Waals interactions. And so basically here, the picture is also in some sense simple. You have water. You have charges which interact with the charges here. So whenever water moves or an ion moves, it brings some electrons with it, and you have interactions. And of course, this was initially a bit hopeless because when you think to the mass of an electron, it's extremely small as compared to the mass of a water molecule. So it was a bit hopeless to find that there could be a momentum transfer between the two. Okay, so that's what we looked at, and actually we looked at this problem together with my wife, and actually with this incredible PhD student, so Nikita Kavokin, now he's professor at EPFL. And actually, if you want to address this problem, okay, let me introduce just one function which I will use a few times. So originally you would say, okay, the dielectric function contains everything. It has all the fluctuations of the charges and dipoles and whatever. Actually, we prefer to introduce the surface response function. And okay, the idea is that you have it's a non-equilibrium problem. So you will have you need a response function between a potential and a charge. And the surface response is just integral over the semi-infinite system. That's why it's a surface response function. And it happens that this you can measure in experiments using Eels experiments. But this is really another way to, in some sense, to write the dielectric function. And something which is interesting, and this connects to the Pendry paper, is that this is actually nothing but the reflection coefficient in electromagnetism. So, for example, in the optical limit, this is simply epsilon minus 1 over epsilon plus 1. So you have good limits, and that's nice to know. Anyway, so I introduced this because, okay, I just wanted to give you the results, and I will discuss rather the consequences. The point is that when you write really at the quantum level the interaction of water, moving water with electrons there, so what you find is something which is in some sense expected. First, you have two types of friction. You have a corrugation, so a static friction. So this is what I call the classical friction. So that's corrugation. And that's exactly what we measure in MD simulation and even in ab initio simulations at the Born-Oppenheimer regime. Now you have a supplementary friction which comes really from the fluctuation of water and the fluctuation of the electrons. And okay, forget about the details. What is important is that, and actually this kind of formula you find the same in solid on solid friction. So that's reassuring. But actually we re-derived it in a different way. And what is interesting is that what this equation says is that you can transfer momentum, so H/Q here, between water and the solid only if the fluctuations, the typical modes of water can overlap with the typical modes of the solid. And this is written here, so that's the susceptibility of the electrons, so it contains all the electronic excitation, and that's the susceptibility of water, it contains all the water excitations. And you have a non-vanishing friction only if these two matches. Now you have other terms. For example, of course, you have this is thermally activated modes, so you have a cutoff at kBt over h bar, so a few terahertz. So it's low energy actually modes. It's not electron volts typically for energy. It's milli-electron volts. So when you look at the modes, so for example, it takes the excitation, and actually the excitation is extremely well known. I mean, people have measured the Debye peak of water for years. And you have a huge Debye peak for water. So this is in terms of this function, but usually it's described in terms of dielectric constant. And this corresponds to all the oscillation of water and the charge oscillation. So this is rather the charge oscillations. And okay, this is a representation versus frequency. I know you can write wave vector frequency is more or less dispersionless over a right range. Okay, that's another way to plot the same thing. Now, if you go to the electronic excitations, you have plenty of excitation, particle hole, etc. But in particular, and this is where we discuss more in details, a surface plasmon. So this is a standard excitation for a Gellium surface. So that's a very standard one. And basically, you will have a non-vanishing friction only if this overlaps this. You see, if the yellow parts are overlapping. Okay, now once you have that, the first thing you take is you go to a book on graphene, because for graphene you can calculate everything analytically, and you take the electronic excitation of graphene. So you have, okay, some excitation here, but you have mainly a surface plasmon, and this is basically charges which oscillate in the plane of graphene. Except that, okay, as soon as the momentum gets high, so where you want to transfer momentum, the energy pops up to extremely high values. So meaning that when water modes are in the range of kBt, so 25 milli-electron volts, and this is much, much higher than the energy, sorry, much, much smaller than the energies of the plasmonic energies of graphene. Now, okay, so that's a bit pointless. Now, what was really unexpected, and actually this goes in the reverse direction, is that we looked at graphite. And actually, graphite is extremely particular, and this is something that we didn't expect. And actually, there were old experiments in the 90s using hills, high-resolution hills, which shows that there is a plasmon on graphite, and the plasmon on graphite has a frequency versus wave vector, which is basically flat up to extremely high value in wave vector. And so nothing compared to graphene. And you see these are experimental data collected in two types of experiments, slight difference in temperature. So you have a fully dispersionless mode, moreover in the range of tens of milli-electron volts. So it's an extremely low energy mode for graphite. And that's very surprising, and actually this was not very well described in the literature. There was basically nothing to describe this. But you can think of the plasmon in graphene, as I was saying, oscillation of charge in the plane. Well, actually, for graphite, you have the surface which goes in the plane, but the surface speaks to the different planes. Actually, it speaks to every two planes. Okay, you have, of course, you have tunneling effect perpendicular, which may transmit charges. And actually, this, you can make a rather simple model where you can think of this dispersionless function as lines. Something you have charges at the top, and this propagates perpendicular. So that's a bit tricky, but that's experimental reality. Now, once you have that, you have you have the two spectra. I mean, you can deduce from the dispersion relation and etc. And then you find a huge difference between graphene and graphite in terms of surface friction. And this is because you have this mode of graphite, which is extremely peculiar, which resonates with the modes of water. And actually, it happens that this value for graphite, for the friction coefficient, is really in the range of what is measured on HOPG. So that's interesting, and actually, this actually also explains that graphene should be extremely different from graphite. Now, why carbon nanotubes? What about the carbon nanotubes? And actually, you can think in simple terms, because when you will curve the graphite, in some sense, if graphite is very flat, okay, these modes where they go up to infinity, perpendicular, and this were multi-wall, I use that, then the friction should be more graphite-like when it's very large radius, very flat. Now, as soon as you will curve them, of course, the layer will be misaligned. And if they are misaligned, of course, you cannot really propagate across the layers. And at the end of the day, you will think that water will only see the last layer, the layer which is in contact. So when it's strongly confined, it goes to the graphene properties. And so, okay, you can make a mix of the two. Okay, that's more phenomenological, but you can make an interpolation in a 1D model, and you find this extrapolation. So basically, this tells you that actually graphene has an extremely low friction because graphene is extremely flat and very dense, and that's what we should measure in graphite. But actually, graphite has, on top of that, a mode which dissipates a lot. So here you see you do not dissipate individually of water molecules with electrons. You dissipate through modes which propagates energy to the infinity. So that's, okay, so we were happy because that was a first measurement of, this connection between quantum, or let's say an electronic properties of the of a confining solid and the friction properties. Okay, so once we had that, we wanted to go a bit beyond. And of course, the first idea would be to make solids with various properties and having solids which do not match the spectrum of water, and then you would, get the mismatch and etc. etc. So that's very hard to do. So we turn the problem around. So we consider rather a liquid for which you can tune the spectrum very easily. And a simple liquid to do that. So let's say you have a solid, which has a spectrum, whatever it is, of electronic excitation, but you will see it's more phononic excitation here. And you have a liquid where varying, for example, the temperature, you vary strongly the typical frequency. And this is a good candidate is glycerol, because glycerol, actually, you see that you change by, you see 12 orders of magnitude going from 180K up to 400K. So it's extremely easy to change the frequency range. So we chose to study the friction of glycerol. It happens that for experimental constraints, we looked at the friction of glycerol on mica. Okay, now mica is an insulating proper system. So you have no electronic excitation, but you will see we will keep a signature of other excitation, which are extremely probably phononic excitations, phonons. So the experiments that we did, so that's a PhD work of Mathieu Lisée with a wonderful student, experimentalist. So we developed for a few years tuning fork AFM. So that's a very nice way of doing AFM. So it's basically using a tuning fork, and basically, you know, if you have a resonance frequency, if you push a bit on one of the prong, you will shift the frequency, so you measure the elastic force. And if you lose quality factor, then of course this means you have dissipation. So this elastic, these tuning forks are extremely sensitive to measure forces. And I mean, I don't, you may know, but people have Leo Gross and people like that, they put this down to the sub-molecular level. So they were able to measure individual molecules using what they call Q+. So it's a tuning fork, but at cryogenic temperature. So here, it's much more modest. It's a tuning fork, the typical one you have in your watch. That's 30 kilohertz, and it costs less than €1. I mean, this. Okay, the electronics cost 70K, but that's no. Okay, and you oscillate, and you have put a droplet of glycerol, mica. We put this in a vacuum chamber to avoid pollution by water, and etc. So, and we vary the temperature by a Peltier between 0 degrees and 30 degrees, just to avoid condensation of water and etc. So it's a small window, but it's sufficient to see many things. So the type of experiments is really much like the experiments done by all the people doing surface force apparatus. So it's really completely equivalent at the end of the day, except it's much easier to do these experiments than surface force apparatus like Elisabeth Charlet, Israel Ishvili, and all these people. So basically, what you do is that you will measure the elastic response, which I will not explore, but also the dissipation. And so you measure the imaginary part of the impedance modulus, and you plot it versus the distance. And if you have no slippage, actually you have the Reynolds formula, a sphere on a plane. If you have some slippage, you have some shift here, and actually there is a small correction. So the shift would be this, that instead of going here, you shift upwards. But actually the Vinogradova formula shows that you actually have actually an interpolation between 0 and this. And so that's what you expect, and from this you can infer the slip length. Okay, so that's all the measurements that we did. So versus temperature. So for example, that's a typical approach retract measurement of impedance versus distance. Actually, you plot the inverse of the impedance versus distance to highlight the 1/d here. Okay, high temperature, then you decrease the temperature. And so, okay, there are many, many points, but you start to see that here you go to a line which goes up to 0, and we have a proper way to measure the 0 here, the distance. But when you get to smaller temperature, you start to feel, you know, you have some curvature here like that. And that's typically a signature of slippage. And actually, these measurements really allows you to measure slip lengths with a high precision. So typically, you have a slip accuracy of a few nanometers. And actually, it happens that for the smallest temperature, here we have a slip length in the range of 200, 300 nanometers. 5 minutes, okay. So that's temperature versus, slip length versus temperature. And, okay, so that's nice. The slip length decrease with temperature. What is more unexpected is that if I come back to the friction, actually the frictions is non-monotonous. So that's very strange because if you had an Arrhenius type of friction, you would have a decreasing friction coefficient. While here it's non-monotonous. It increases again at high temperature, and this is not expected at all. And okay, so another way is that the temperature actually fixes the typical mode for the typical modes of the glycerol. So you can have a plot of friction versus the relaxation rate. So to understand that, again, we turn to this connection between the fluctuation of the liquid, so glycerol, and the fluctuation underneath. And the fluctuation underneath here are more, we expect to have phonons, typically, in mica. So if you go back to the fluctuation-induced friction, you write it simply in terms of the modes of the liquid, the modes of the solid, and you have a formula which looks a bit like the quantum friction formula, but here it's different. It's a spectrum of solid and liquid, not the charge spectrum. And now, okay, you do the same job. You have the friction and you estimate the solid and the liquid. The solid has two contributions, a static corrugation at 0 frequency and a phonon-like. And the liquid is a Debye-like, we assume a Debye model which works perfectly with a characteristic frequency omega alpha. Then you have two contributions. One, the friction here is basically, it's easy to see that the friction coefficient will scale like the relaxation time, so the inverse of the frequency. And that's typically the classical friction. But now this other dissipation with the phonon modes actually puts forward this terms omega alpha here, while the frequency is fixed by the phonons. And this term actually is proportional to the frequency itself. So you have two contributions, one which is 1 over the frequency of glycerol, and one is proportional to the frequency of glycerol. And actually, when you plot that, you obtain this kind of graph, and okay, this seems to work quite nicely, and also explain why you have larger friction when you go to higher temperature, because in some sense you excite more and more the phonons, and you see them more and more. Okay, so with this, we did plenty of things. We continue. Actually, what is nice is that you have a perspective of friction and flows in Fourier space, in some sense, in the excitation space. So we try to push this idea, and okay, I will not discuss it because I will not have time, but you can think of conversion of energy from mechanics to electronics without any electrochemical stuff, which is nice. You can also think of flow tunneling, so the water flow going through excitations and then going back to a flow. So you have really the momentum tunneling across solid systems, etc. So let me skip this part, but to go to the, okay, I was too ambitious, clearly. Sorry for that. Okay, so that's what we do. So just in 2 minutes, and then that's the end, I would like to okay, that's fundamental basic science and etc. But I was always a bit stressed by the fact that okay, first we have to show that we are useful as scientists sometimes, and as I discuss a lot with industry people, sometimes it's a bit harsh to show that I'm useful. So can we, in some sense, we have here a new phenomena. Can we use this phenomena to make something useful? And actually, what is extremely hard, I find, is what I call the technology killer, is that in all these systems, you have two infinites. You have plenty of new phenomena at nanoscales. But of course, if you look at the desalination plant, you have membranes in the range of millions of square meters. So you have to implement this phenomena at millions of square meters. So that's a huge challenge. And that's basically why you kill whatever we invent in this room will be killed, at least in this nanoscale. But actually, this is what we try to tackle with what is called osmotic power. So very briefly, osmotic power is that you take rivers going to the sea, and you have the entropy of mixing, which you can harvest. So that's really the dream of harvesting entropy. And there are some technologies, in which there were some in Norway, there is one in the Netherlands, but we are really too inefficient and very expensive also. So to produce, so that's an energy which is untapped, and the reservoir is huge. Huh? It's up to 2,000 2,000 gigawatts. So it's absolutely considerable. Now, so what we did, so I will make a long story short, that we looked at these problems from nanofluidic perspective. So 10 years ago, we looked at the flow, ionic flows of across boron nitride nanotubes, and we found extremely large ionic currents whenever you put difference of salinity. So we say, oh, that's that could be very, very useful for osmotic energy. And actually, this was a diffusion osmotic process and new materials. So then we screened other materials, and we said, okay, let's scale up. So, but scaling up was extremely difficult. So we looked at other methods. For example, we try to avoid electrodes, which are a pain, etc. But actually, at the same time, and this is what I went to, is that we created a startup 10 years ago, 2015, on these topics. So first, the startup worked with 3 people together with us, and we screened materials to find what could be a membrane which use what we found here, but at a large scale. And actually, it took 10 years, but they found materials. So it's a biosource material. It's basically cellulose, but a particular cellulose, which costs nothing, so less than $1 per square meter. And it's very powerful. So in the sense that, for example, so that's typically, we go from 1 nanotubes to this is an osmotic, individual osmotic reactor, we say. So that's typically where the energy is produced. That's the scale. And now typically they have 20 square meters. And the scale of 20 square meters, they bypass what we call the break-even in osmotic energy, which you have to bypass 5 watts per square meter to be commercially scalable. And so this they produce, and now they are building a pilot plant on their own. So my message is that, okay, and we try this method on various problems, various phenomena that we found. And I think it was interesting to use a startup as a tool, not only an economic process, but say these startups, they are doing research and science with a specific mission. So they are really doing science, but with a mission which is fabricating an osmotic reactor. And so 10 years after, they delivered. And so I would love that we have the climate crisis. So I would love to generalize this. So I tried in France, so try to create an innovation center, mixing scientific people, engineers at high level with some kind of mission. So we made a call of action for Manhattan Project for the ecological transition. So of course the Greens, they were completely upset by the Manhattan wording. But at the end, it's really true. Manhattan, in a few years, they delivered, going from a theoretical idea to a process. So, I mean, okay, we are all here scientists, so I would hope that, I mean, at some point people realize that this is really important to do that for the future. And with this, I stop. Sorry for the...
Questions. Thank you for a wonderful talk. Patrick.
Yeah. No, that's purely, here it's purely classical. But it's really the idea of excitations. Actually, honestly, we did these experiments first to have a benchmark, and the benchmark happened to be interesting. So, because our point now is to go back to plasmons and etc. So now I have a colleague who fabricate plasmonic surfaces, extremely flat, etc. So now we are going back to electronic excitations, but here it was purely classical. It would change a bit, yeah, sure. So for example, in the simulation, it's easy to do, and we did it. We played a bit. We made super heavy water, so to shift the spectrum, and indeed you see a difference. Okay, in the experiments, okay, yeah, it's difficult to make. Yeah.
Is it really just mixing pure water with salt water and then putting a membrane through and using, I didn't really understand that last.
The osmotic. So, yeah, I was very short. I just wanted to make the point of startups, but indeed, I mean, in some sense, you want to harvest the entropy of mixing. So the simple way is to use a membrane, which is semi-permeable, and then you have the osmotic pressure. But this works very badly. I mean, the efficiency is very low. So another way is to have anion and cation selective membranes with a gradient. So then the positive go in one direction, negative in the other, and you create a current which you convert in an electronic current. So that's called reverse electrodialysis. So René looked at that, and there is the setup in the pilot plant in the Netherlands is like that. So here it's in between. So because the membrane is very different from the one which is used in the Netherlands. So that's this cellulose-like membrane.
Fantastic.
Thank you.
Any further questions?